All right, let's take a look at section 15.1, which covers double integrals. So the things that we're going to look to do in this section, we'll define a double integral as well as the average of a two-variable function. We'll approximate the double integral using Riemann sums, pretty similar to how we would have approximated integrals back in Calc 1. And then also we're going to use some simple geometry to help us out in calculating a double integral when it applies. So starting with that definition, in a two-variable function, if I want to take a double integral over some region R, that'll ultimately end up giving me a volume. Back in Calc 1, we integrated just in one direction and we got an area. So now in Calc 3, multivariable calculus, where we take a double integral, we'll integrate over an area instead of just along a single line, and our final result will be a volume instead of just an area. So we've got that figure down below that shows the region that we'll want to integrate over in this for an example double integral, and we'll stick with just a rectangular region for now, because if we're working in rectangular coordinates, a rectangular region is far and away the easiest region to integrate over. And so you can kind of see where that volume fills out, being the area that's just kind of the volume that ends up inside here. That should be the volume that we end up calculating. But if we attempt to approximate that area using something similar to a Riemann sum, so say, for example, we'll use 6 rectangles of width and length of 1 to approximate the volume under the plane 6 minus x minus y over the rectangle R, determined by x being between 0 and 3 and y being between 0 and 2. So I sketched out just the region that we would use, which would be this region between 0 and 2 in the y-axis and 0 and 3 on the x-axis. And that ends up giving us 6 rectangles, or in this case 6 squares, that we're going to want to use to approximate the volume of this overall shape. So if we just break down one of these rectangles for a moment, say the one that's between 1 and 2 on the x-axis and 0 and 1 on the y-axis, and break down what that looks like, it should be this rectangular box pictured to the right, where, I suppose, maybe it makes sense that also that bottom rectangle should be shaded in blue. So when we did Riemann sums back in Calc 1, we looked at both right-hand and left-hand Riemann sums, as well as upper and lower sums, where the way that we'll approximate this is by within the rectangle that I've shaded. I just need to pick some point to be the height of the box that we end up using. The text talks about using the midpoint of every box, although in this particular example, I'm just going to pick the upper right corner to be our approximation for the height, which means the height that we will use to calculate this particular rectangular box would be f of 2, 1. And we know that the width and the length of the base rectangle should be 1 in each direction, which means that the volume of each of these 6 individual boxes that we'll be using to estimate the volume would just be equal to the value of the function at whatever point we choose. And again, I'm going to choose the upper right point in each spot. So if we want to make some approximation about what we're doing here, the double integral over our region of 6 minus x minus y dA should be equal to f of 1, 1 plus f of 2, 1 plus f of 3, 1 plus f of 1, 2 plus f of 2, 2 plus f of 3, 2. And we can multiply all of that by 1 and by 1 for the length and the width of each rectangle. If we plug all of that in, I think we should get 15. At least that's what I did when I plugged each number into that function. Feel free to verify that for yourself if you like. But again, for this approximation, we'll just use these rectangular boxes, pretty similar to how we would have made rectangles back in Calc 1 when doing a Riemann sum. So if we take a look at what that might look like over some general region, figure 4 and figure 5 does a fairly decent job of sort of visualizing what it is that we're doing. We're taking our region, which is shaded in orange, and we're going to create a rectangular box in each one of those rectangles along our region R. And use that to create a whole bunch of boxes that will add up and say that that approximates the volume of the shape. As we can see over in figure 5, when we filled out all of those rectangular boxes, we get a shape that looks like it'd be pretty close to the volume of the shape that we're actually trying to get. So we'll go ahead and make ourselves another definition. So as long as we have an integratable function f, then we can define the double integral as the limit as n tends to infinity of the sum from 1 to n of delta a times f of xi star times and yi star, where n will be the number of subrectangles that we break down into. That xi and yi just represents some point within each of those rectangles that we divided ourselves up into, so that we can get a height for each of those rectangular boxes. And delta A will be the area of each subrectangle, just like we would have used delta X back when doing Riemann sums in Calc 1. So we break all that down, take a limit as we use an infinite number of boxes, and we should get to the exact value of that double integral. So the average value of a function over some region, as given by the equation below, where we'll just take the double integral of the function over that region, but then divide by the area of the region. We'll see quite a few more of those problems in the next section, so we won't dwell on them too long here. So a couple of properties of double integrals that'll be nice to use. If we're adding two functions on the inside of a double integral, we can separate them out into two separate double integrals, similar to the summation rule that we had for single integrals. That one will still hold for us. Also, if we're going to multiply some function by a constant multiple inside of a double integral, we can pull that constant multiple all the way out and just deal with it after we do our double integral. And if we have that some function f is greater than or equal to a function g for all points in our region, then we know that the double integral of f will be greater than or equal to the double integral of g for that whole region. All right, and let's take a look at another example. This is one where we are going to want to use just some simple geometry to help us out. So we're going to find the double integral of 4 over a region, where that region is all x and y that satisfy the equation x squared plus y squared is less than or equal to 9. So what we're really looking at here is if we just break down that region right here, this is just a circle of radius 3. Right, and we're filling in, and since we're taking the inequality there, where x squared plus y squared is less than or equal to 9, that's all points inside of that circle and along the boundary of that circle. Less than for all the interior points and equal to for the boundary part. So that's going to be our region, and we're integrating the function, which is just 4. So it should just be 4, a height of 4, times the base, which is that circle of radius 9, ultimately gives us a cylinder. Oop, I think I said 9, but I meant 3. So we'll ultimately get a cylinder that has a base that's a circle with a radius of 3 and a height of 4, which is a relatively simple calculation. So that volume should be 4, which is the height, times the base, which should be pi r squared. So pi times 3 squared. And we can simplify that to 36 pi. And that should be the volume of that shape. Speaking of simple shapes, if we head back up to the first example real quick. So we approximated an area here, but we could have used some simple geometry to get an exact value for this problem as well. Since we're just looking at a plane that's a plane that is above the xy axis, the shape should just be a pyramid that's stacked on top of a box. And those are two polyhedrons that we could relatively simply calculate the area of if we felt so inclined. In the next section, we'll start looking at some less easy to calculate areas and stuff that we'll actually need to use integrals for.